All right. So group number 13, the Boron family.
All right. All right, so group 13, or family 13, again, those terms are interchangeable. Boron, aluminum, gallium, indium, and thallium. All right, they do not occur in element form, except for aluminum, which is aluminum foil. They are scarce in nature, except for aluminum, which is most abundant metallic element.
That seems to be an exception.
Yeah, it does. Now, 3 valence electrons. Okay, so this one's going to make you think a little bit more. What if we covered up that 1 in the family 13? Oh, look at that. 3 valence electrons. How about that?
I think I can do that.
I think I could do that. Are metallic solids, except for boron, which is a solid metalloid. It's on the stairs.
Okay, it's on the stairs there.
So with the exception of aluminum, anything on the stairs is going to be a metalloid. Soft and have low melting point, except for boron, which is hard and has a high melting point. Chemically reactive at moderate temperatures, except for boron, because it's a metalloid.
Exactly. Okay.
All right.
And on trinium, element 113 is thought to have similar properties to these elements. They're still working on that, though, because it's extremely radioactive.
All right.
It doesn't exist very, very long when they make it.
Okay, the carbon family. Carbon, silicon, germanium, lead, and quadium. Ooh, I said it.
Yeah. And these names that are down here, the fun part is they're just another language. 1, quad means 4, so it's 114.
Okay.
That's all the name actually means right now, because they haven't figured out what to call it yet. But group 14 has carbon, silicon, germanium. Oh, you just said that, didn't you?
Science is repetitious.
Science is repetitious. It does include a non-metal, carbon, 2 metalloids, silicon and germanium, and 2 metals, tin and lead.
Yeah.
They vary greatly in both physical and chemical properties because there's the 3 different types of elements there. And they occur in nature both in combined and in elemental form. So they're both going to be compounds and elements. They all get 4 valence electrons. Go figure. You can actually predict that.
Yep.
And they're relatively unreactive. They don't really like to react necessarily. They're okay all by themselves.
Good. Nitrogen, group 15. I'll bet this is going to have 5 valence electrons. Yep, there it is, 5 valence electrons.
5 valence electrons because they're group 15.
Nitrogen, phosphorus, arsenic, antimony, bismuth, and I'm not even going to try the last guy.
On pentium.
Thank you, Mr. Kane. They range from very abundant elements like nitrogen and phosphorus to relatively rare elements like arsenic, antimony, and bismuth. Oh, arsenic's really rare, and I like that one.
Yeah.
That's too bad.
It's good to have in your tea every once in a while, isn't it?
Not my tea, somebody else's.
You just have. I've heard that people who really try arsenic in their tea only try it once.
I'll bet. Nitrogen is a gas at room temperature, isn't it? That's why it's red.
That's right. But all the rest are solids at room temp.
And it's a diatomic, isn't it?
And the interesting part here is the ones at the top, nitrogen and phosphorus, tend to be more abundant, and the ones near the bottom tend to be more rare.
Oh, okay.
It's probably a good thing in the case of arsenic.
Yes, that's true.
Group 16 is oxygen family, and group 16 you can predict has 6 valence electrons.
Oh, yep, that's easy.
So we've got oxygen, sulfur, selenium, tellurium, and polonium, along with hexinium. They occur naturally as elements and in combined states, just like most of these other families on the right side of the periodic table. Consists of 3 nonmetals, oxygen, sulfur, and selenium, a metalloid, tellurium, and a metal, polonium.
All right.
We talked about the valence electrons. They also tend to exist as diatomics. So
polyatomics.
And polyatomics, yeah. Not just diatomics, but polyatomics also. So oxygen also comes as ozone, O3.
One is oxygen gas and one is ozone, isn't it?
Z-O-N-E.
Okay.
Yeah. And this is oxygen, gas. Okay. We've also got S6 and S8, which are 2 different forms of sulfur, and selenium-8, which is a form of selenium. Okay. They don't like to come as single atoms. They like to come in.
And the last 3 aren't part of the diatomics because they're not 2, right?
Right. And ozone isn't a diatomic either.
Right. Ozone's not. Oh, the last 4 then, yeah.
Technically, it's a triatomic.
Yeah, triatomic. Yep.
List all the triatomics! Oh, wait. Just the diatomics.
Just the diatomics.
All right.
Halogens. Family number 17 is the halogen family, and without me even looking, I'm not looking, if I cover up the 1, I am going to bet that everyone in that family will have 7 valence electrons. Am I right?
That's right.
I
Yep.
can open my eyes now?
You can open your eyes now.
Awesome.
Good job.
Fluorine, chlorine, bromine, iodine, and astatine.
And septenium.
And septenium.
All right. So the halogen family, guys, comes from the Greek word halo, which means salt. Okay. These guys are usually found in salts, kind of like the alkaline earth metals. Okay. You can look more about that if you like.
So they're not terribly abundant in their elemental form?
No, they're not abundant in their elemental form because they're so reactive. Matter of fact, one of the traits of this is that they are the most reactive non-metals.
All right.
Remember, the most reactive metals were the alkali metals?
Yeah.
These guys are on the almost the complete other side of the periodic table.
Okay.
Almost. They're the 17th group rather than the 18th, but they're the most reactive non-metals we've got. They're found in rocks of the Earth's crust, and they're found dissolved in seawater. You know, get this, guys. They form salts, so the salts that make up seawater have these elements in them.
Oh, okay.
They exist at room temperature in their elemental form when we make them in their elemental form as a gas, fluorine and chlorine both, as a liquid for bromine, and as a solid for iodine and astatine.
So is that why the bromine symbol is blue, kind of like liquid form, like water?
Exactly. That's why it's blue and red for, gas.
And chlorine gas, the element chlorine gas, wasn't that used in World War I as mustard gas?
Yep, that was mustard gas. That is a war gas,
Okay.
and that's illegal these days to use in wartime. It's also the reason why you don't mix your household chemicals together and try and make up your own household cleaners.
Yep, that would not be wise.
Oh,
Highly reactive, which you did verbally say.
all right. Last group to talk about, Group 18.
Noble gases.
Noble gases. They're called the noble gases because back in the days of kings and queens, they were called nobles. And when they first discovered the noble gases, they realized that none of the noble gases reacted with any of the other elements.
Okay.
So kind of like the nobles wouldn't do anything with any of their
All right.
peons.
Yeah.
Yeah.
God
All
forbid they mixed with the other classes.
Exactly.
Okay.
But you've got helium, nice one for parties.
Uh-huh.
Also for the blimps that we currently use.
Yeah.
Like the Goodyear blimp, at football games.
All right. Well, that's what they put in balloons, yeah?
Yeah.
At party stores. Okay.
Neon, argon, krypton, xenon, and radon. Oh, by the way, Miss G, it's Group 18, so guess what's important here?
8 valence electrons?
There we go, 8 valence electrons.
With the exception of...
Oh, there is an exception in this group. Helium, how many valence electrons does helium have?
I'm assuming 2, because he's only got 2.
Yeah, so this is the exception. Only 2 valence electrons for helium.
All right.
The rest of them have 8, though. These are all found in very small quantities, minute quantities in the Earth's atmosphere. Helium can be obtained from natural gas wells where it's accumulated as a result of radioactive decay. That's kind of interesting because the world's helium supply are just going up in the air. Every time somebody lets a balloon go, we lose it. We lose the helium. So there's less and less helium on the surface of the Earth here. They're actually talking about one of the reasons to go back to the moon is to mine helium because there's a lot of helium in the moon's rocks.
All those future parties need helium balloons.
Exactly, and they use it as a refrigerant. They use it for making lasers. There's a lot of good uses, good scientific uses for helium, and it's just becoming more and more rare.
Now, is radon the stuff they had to get rid of? It was in buildings and stuff like that?
Radon is actually it's a gas that creeps up through cracked foundations in buildings. So it's not one you can actually get rid of. It's one that comes from below the surface of the earth that kind of trickles through the soil. And if you've got cracks in your foundation, you should probably go to the store and get a radon test kit just to check.
All right. I've thought I heard that name before.
All of these noble gases are what are known as atomic.
Meaning one.
Meaning one atom.
So unlike the diatomics, these guys are monatomics. Okay.
That'd be a fun test question, don't you think?
I think that would be awesome.
List all the monatomics now.
Ooh, that'd be tough.
It wouldn't be too hard. Not now that you know something periodic.
True, I guess that's right, yeah.
All right.